Assalamu alaikum, dear students. It is the second part of my lecture number 2. In the previous lecture, we studied about zeroth order reaction. Dear students, now we will study in detail about the first order reaction. Same it is just like first order reaction, the examples of first order reaction, rate constant expression of first order reaction, results, and units of the rate constant. Dear students, what is meant by first order reaction? First order reaction, it is a chemical reaction in which the rate of reaction is directly proportional to the concentration of a reactant raised to power 1 is called first order reaction. A chemical reaction in which the rate of a reaction is directly proportional to the concentration of reactant raised to power 1 is called फर्स्ट ऑर्डर रिएक्शन। तो फर्स्ट ऑर्डर रिएक्शन से मुराद एक ऐसा रिएक्शन है जिसके अंदर रेट ऑफ रिएक्शन रिएक्टेंट की कंसंट्रेशन जिसकी पावर 1 हो उसके डायरेक्टली प्रोपोर्शनल होता है। डियर स्टूडेंट्स, अगर हम इसकी एग्जांपल्स देखें, देन द फर्स्ट एग्जांपल इज वेरी इंटरेस्टिंग। यू नो अबाउट द disintegration of some radioactive elements. The decay of radioactive element also follows first order reaction. For example, disintegration of radium-226 into radon 222 and alpha particle or helium nuclei. This reaction totally follows the rate constant expression of first order reaction. So you can apply this concept to all other remaining radioactive elements. Whenever a radioactive element decays, then it will follow first order reaction. Our students who have studied biology and zoology, botany, they have already learned this point. When a bacteria grows, then what happens? That a bacterium cell divides into daughter bacterium cells by mitosis, by meiosis, or some other, whatever. Anyhow, when a bacterial cell grows into daughter cells, then the growth of a bacterial cell into the daughter cell, this also follows first order reaction. A very important reaction, the inversion of cane sugar, sucrose, into glucose and fructose. This reaction takes place when you react dilute HCl. So when you react sucrose with water in the presence of dilute HCl, then glucose and fructose are produced. This hydrolysis of cane sugar is also followed by first order reaction. So the first order reaction, it is a chemical reaction in which the rate of reaction is directly proportional to the concentration of reactant raised to power 1. And the examples of the first order reaction are the disintegration of radium-226 into radon 222. This integration of radium into radon and helium nuclei or other radioactive elements into daughter nuclei. This is the example of first order reaction. The growth of a bacterial cell into daughter bacterium cell, this reaction is also first order reaction. Inversion of cane sugar into glucose and fructose, it is also example of first order reaction. Dear students, now we will study the derivation of a rate constant expression for the first order reaction. To understand the kinetics of first order reaction, let us consider that a reactant A is converted into some products. When the reaction starts, when time was 0 second, then there were A mole of the reactant A and 0 mole of the product. But when some time is spent, after some time, when time is equal to t second, then what happens? This A changes into product, and the concentration of product produced is X, while the remaining amount of the A is the A minus X. For such type of reactions, when we write the expression for rate of reaction, then rate of change of concentration of X with respect to time dx over dt is directly proportional to A minus X. When we eliminate this proportionality, then this expression becomes dx over dt is equal to k into A minus x, and this k is called rate constant. And in the next lecture, we will find out the value of this k. Dear students, this equation dx over dt is equal to k into A minus x is the differential rate equation for the first order reaction. So, we will integrate it by separating the variables, and when we applied integration rules to this equation, then this is the sign of integration into dx over A minus x. This A minus x was in the right hand side of this equation. When we separated the variable, then the equation became dx over A minus x is equal to k into sign of integration into dt. According to the rule of integration, this sign of integration and dx has been replaced with negative natural log. Negative or minus natural log has been written here by using the rule of integration, in which this sign of integration into dx has been replaced with negative natural log. And the main important rule of integration is when we apply integration to the right hand side of this equation, then this sign of integration with the derivative d will be replaced with plus c. So c is here integration constant. So when we integrated the equation, we got equation 5.3 minus log natural into A minus x is equal to kt plus c. In this equation, natural log is obtained when we multiply simple log with 2.303. A is the initial concentration of reactant, x is the concentration of product after time t, k is the rate constant which value has to be determined, t is the time, and c is the integration constant. When time was 0 second, then the value of x was equal to 0. If we put these values in equation 5.3, then the value of c will be calculated negative natural log into a minus c. C was equal to 0 because x was equal to 0. So the x has been replaced with 0. T was equal to 0 plus c. So when we take the value of t equal to 0 and x equal to 0, then the value of integration constant c is minus natural log a. If we put this value back into equation 5.3, then we get the value negative natural log into a minus x is equal to kt minus log natural a. Now, if we separate the natural log values and kt, then this natural log a, that is minus here, will be positive on the left hand side. So if we rearrange this equation, then natural log a minus natural log a minus x will be equal to kt. K is the rate constant and t is the time. So kt will be equal to, according to rules of the logarithm, if the value of the log m minus log n, then we will write log m over log n. So this equation will become equation 5.4 as log natural a over a minus x will be equal to rate constant k into time t. So from the equation 5.4, we will be able to find out the rate constant expression for a first order reaction. Dear students, when we studied the derivation of rate constant expression for the first order reaction, then A changed into product when time was 0. Second, there were A mole of the reactant A and 0 mole of the product. After time t second, there were produced X mole of the product and the remaining amount at the time t was A minus X of the reactant A. After applying the rate constant expression dx over dt, we find out dx over dt is equal to k into a minus x. K was the rate constant. After applying integration, we obtained equation 5.3 minus log natural into a minus x is equal to kt plus c. By applying the initial conditions when time was 0 and then x was 0, so the value of c becomes negative log natural a. After putting this value back into equation 5.3, here in this place, we got the equation 5.4, according to which the product of rate constant k into time is equal to natural log a over a minus x. So this equation 5.4 is very important to find out the rate constant expression for a first order reaction. Now, dear students, we will study some results related to this equation 5.4. This equation 5.4 is the equation of straight line that passes through the origin, where natural log a over a minus x is the dependent variable and t is the independent variable. Here are two types of variables, dependent and independent. And dear students, remember, when you find out rate constant expression for the first order reaction, then the natural log a over a minus x will be independent variable while time t will be the independent variable. If we draw a plot between a minus x along y-axis and time t along x-axis, then we obtain the equation 5.1, which shows the variation in the available concentration of product with time. But if we plot the values of x along y-axis and time t along x-axis, then we get a straight line that curves like this one. So both these graphs can be applied with reference to the equation 5.4. You either can draw a graph between log natural A and time, or log natural 1 over A minus x and time, and ultimately you will get two types of different plots. The unit of the rate constant K will be per second. Dear students, if I summarize the main points of the first order reaction, then you have to remember following important points. Number one, that first order reaction is a chemical reaction in which the rate of reaction is directly proportional to the concentration of reactant raised to power 1 is called first order reaction. The examples of the first order reaction are the disintegration of radium into radon, growth of a bacterium cell into daughter cell, inversion of cane sugar into glucose and fructose. When we derive a rate constant expression for the first order reaction, then we ultimately obtain an equation 5.4 according to which log natural A over A minus x is equal to rate constant K into time, and this is the equation of straight line passes through the origin. Dear students, thank you very much and take care of yourself. Allah Hafiz.